All right, folks, welcome back. Um, any questions about what the semester is going to look like, expectations, um, anything like that before? Oh, one thing I had forgot. Um, just because we are going to be using real life data and that some of these examples will be used again uh, for additional cohorts moving through. I'm going to send you two agreements I have people complete for the course. First one is a data use agreement that just says, hey, you're going to be using data that's been collected and that's based on real data sets. And it's just that you're recognizing that this isn't something that you should try to publish anything with. One, because it's not yours, and two, I've often fooled around with it a little bit to get it to do things that I want to do for didactic purposes. So I'm going to send you a Qualtrics link. It just goes through and it's agreement. Just type in your name and say sign and date that. We would normally do this in person, but we obviously can't do that. The other thing is confidential agreement form, just saying that you recognize that I'm going to give you information. You're going to have problem sets. I'm going to give you intensive feedback on problem sets so that you know where you got right and what you got wrong, but that those are your materials and not materials to be shared with other people or things along those lines for the purposes of potentially giving someone else sort of down the road an advantage that other people don't do. So just recognizing that even once you're done with the class, if you were to just say to give all your problem sets to somebody else, that would be a big problem and would require sort of steps to be taken. So I'm going to send out links to both of those. Just go through. It'll be quick and easy. Just go through, read it, make sure that makes sense. Let me know if you have any problems. But otherwise, we'll get that taken care of, or that will be sort of taken care of. Okay. Questions? Okay, cool. All right. So today, for lecture stuff, going to go through basic fundamentals. A lot of this stuff is probably going to be stuff that's review, and that's good. We'll move through stuff pretty quickly so that I don't bore you with things that you already know. However, just given the range of abilities that people are coming in with or background that people are coming in with, want to make sure that we're all on the same page with basic concepts and things. So again, what we're going to do is talk about primary purpose of quantitative method statistics, what we're trying to accomplish with this, and then just working through some basic fundamental concepts that you'll have should have covered in your undergraduate coursework. So when we think about the purpose of statistics or quantitative methods, a number of things that we're trying to do. These are fallible tools that can be misused pretty easily. This is one of the things when I'm reviewing papers, I see people using techniques or trying to use techniques that they probably don't know how to use them correctly. It sort of feels like running with scissors. Hopefully, once we finish up with this, you will not be one of those people. And people will say, oh, well, people just lie with statistics, so on and so forth. Yeah, you can. But if you know the nuts and bolts, thinking if you're approaching this from a technician standpoint, you'll be able to very easily identify when people are trying to play around with numbers and things like that. But good things about statistics, things that it helps us do, is we're often working with large quantities of information. And what our statistical methods do allow us to go through and start to draw conclusions from data that would otherwise be difficult to kind of just eyeball on your own. Okay. So if we're, say, have this table here, how many, this number of drinks per month in, let's say, a random sample of students. Natalie, if you're looking at this, how much do students drink here? Is this an easy thing to reduce down and sort of get a good sense just based on eyeballing those numbers?
Not quite. Not very easy.
Yeah, it's kind of tough, right? And this is a very, very small set, right? As we start to get into very large sets, to just go through and eyeball things starts to become difficult. So what we can do with just even our basic descriptive statistics is start to reduce things down that start to make a little bit more sense, right? So right here, I'm saying that from these data, we are seeing that the mean of the sample is about 15.4 drinks per month. Has anybody here ever done alcohol research in a lab or anything like that? No alcohol researchers?
I'm sorry, I have.
Yeah. So, Allie, 15.4 drinks per month. What do you make of that number? Is that big? Is that a lot? Is that a little? What would you think?
Like, I don't know, like a little over average, or I
Yeah.
don't know, like not a ton.
Yeah, it's not a ton, but it's not none, right? We're thinking about a drink maybe every other day. If these are undergraduates, I'm not sure how that's. I'm pretty sure that's probably not how that alcohol is being consumed. Is a beer every other day, right? So we would need to know a little bit more about this, right? But what we can do is start to get a sense for the sample. So, Ali, what does if I say the mean is 15.4 drinks per month? What am I talking about in terms of the mean?
You mean like the average?
Yep, just the average, right? So the arithmetic average of this sample is about 15.4 drinks. But maybe I want to know, so is everybody sort of right at that level, right? So what I might want to know is a little bit more about the spread. So I see here that my standard deviation is about 12.4. Riley, is that a lot or a little?
I mean, I feel like it's a lot because it's almost the same as the mean.
Yeah, right. So we would say, based on these data, on average, if I had to just guess how many drinks a random person in this sample drank, my best guess is going to be about 15 and a half, right? But I could be off on average anywhere plus or minus 12 drinks, and that's well within the range of the sample, right? And so there's a lot, I'm reading that there's a lot of variability in this, right? And what about this range? How do I interpret the range, Riley?
How do you interpret it? Well,
Yeah.
it's like it'd be like the person who didn't drink anything and the person who drank the most.
Yeah. So these are my anchors, right? So we've got, it's not giving the min and the max, but we've got sort of a range of 40, a difference between 45 drinks between my most high and my least high, right? And so basically with just a few numbers, what I can infer from this sample, assuming this is a random sample, is that undergraduates are drinking, right? But the level at which they drink is very variable, right? And it jumps around quite a bit. And as we start to get good at this, we can start to quickly make some inferences based on just a few set of numbers, right? We can also go through and graph things. If I go through this graph I keep lasering my screen here, but you guys can't see what I'm pointing at with my laser on account of. So I've yet to develop theory of mind and recognize that you don't all see exactly what I'm seeing at all points in times. But these graphs are a nice way of going through and showing kind of what's going on with drinks. Robert, if you're looking at this graph, is there anything else about this drinking behavior that you can start to glean from that histogram there?
They're pulling modal data and examining that there's a number of drinks between 0 and 5, 5 and 10, and then also 35 and 35.
Yeah.
So a lot of people drinking either very little or kind of that average.
Beautiful.
Above average.
Yep. Yeah. What it looks like, what I'm getting from this is that it looks like I've got maybe a couple of different groups here, right? Suggesting that maybe that mean value isn't a really good representative of what's going on in terms of the actual behavior. I've got a lot of people who are not drinking at all or very, very little. And then I've got another group of people who are drinking quite a bit. And then we've got some of the outliers there, but less people kind of falling in between that range, right? So this is where graphical representations can be very, very helpful in terms of capturing aspects of our data that are sometimes missed with just our summary statistics. Yeah. Our statistics also do a nice job of giving us some quantitative measures of the association between different variables. Okay, and this is hard to pick out with our eye. So let's say what we've done is we've got 334 individuals exposed to traumatic injury. And 248 of those people are reporting chronic pain at least 12 months, and these are car accident folks, right? So 248 individuals of the 334 are still reporting chronic pain a year out of the accident. And what we're interested in looking at is the extent to which pain status is related to trait level anxiety. So on average, do people with higher levels of trait anxiety tend to demonstrate more or less sort of fall into this pain category? Okay. I jumped down. Brittany, taking a look at this graph and some of these statistics, what might we conclude from this?
So does the mean trait of anxiety, like, is that on the left side? Is that what that's saying?
Yeah, that's our anxiety levels.
So the higher, well, they look pretty similar actually to me, like no pain versus chronic pain, but the chronic pain people are a little bit higher in anxiety.
Yeah, looks like. And how much confidence do we have that in the larger population, our pain people are experiencing or reporting higher levels of trait anxiety?
The 95%, is that the CI?
Yeah, some of that stuff in there. Yeah. Mm-hmm. Yeah. So if I go through and I take a look and I see the mean difference here. So this is levels of anxiety in the confidence interval for people without pain. This is our average level and confidence intervals around people with chronic pain. But then the difference between these two is about a difference in anxiety point about 5 3/4 points on my measure, right? But my confidence interval says supported values range anywhere from about 2.5 to 9, right? Now, if I know a lot about STAI scores, I could probably sort of glean something whether or not that's a big difference or not a big difference. But if I go through and I take a look at my statistic here, I'm seeing a very low p-value. I've got an effect size of 0.44, which suggests that there is sort of odd difference. It's not super large, but I can be fairly confident that, yeah, it looks like these two groups in the larger population, if I were to pull all individuals who have been in accidents and look at people with and without chronic pain, that I would probably see some difference between those individuals with no chronic pain and those individuals with chronic pain in terms of trait level anxiety. And my guess would, at least the data that I've got here says that difference would probably look somewhere between 2.5 to 9 points, right? So a nice way to go through and summarize. And so I can go through and I can run this with a means-based test. So anybody, what type of test have I run here? Anybody know? So this is just our t-test. This is just our group-based t-test, just our difference here, right? What I can also do is I can also run this as a correlation, right? I can look at the association between pain status, yes, no, and trait level anxiety. And if I run this as a correlation, I get a correlation of 0.4. Okay. Someone familiar with correlations or comfortable with correlations? Is a correlation of 0.4, is it a lot? Is it a little? What do we think?
Is it medium?
Yeah. It's kind of it's a medium-sized correlation. It's sort of definitely something, right? Stronger than a lot of correlations that we see in behavioral sciences. And again, we've got our confidence interval saying that our data would support in the larger population. Again, if we could get everybody who had been in a traumatic accident and look at the relationship between chronic pain status and trait anxiety, our best guess for what that correlation is about 0.4. But our data are supporting anything ranging from 0.3 to 0.48. Okay, and again, this is a pretty hefty correlation going on right here. But is one of these a better way to present these data, either in a correlation or a t-test? What do you think?
I mean, it's definitely, I think, easier to see in a t-test than the correlation.
Yeah. I agree, Allie. It's easier to kind of see this difference in a t-test. just kind of given the question, it kind of makes a little more sense to see it there. But the correlation is the exact same thing, right? It's capturing the exact same association. It's just presenting a little bit differently. And so what we hopefully will get out of this course is sort of ability to work back and forth between these flexibly. I agree. Most time, sort of the t-test is going to be the more intuitive way to present this, but there's going to be times when the correlation might make more sense depending on the model, and sort of knowing that these two things are interchangeable is going to be important. Yeah. So another thing that we can say in terms of our purposes of statistics is giving us a standard language. Okay, if I say that I've run a t-test, and this is the difference between these groups, I should be able to talk to Erica, who's in a lab on the other side of the world, and say, I've run a t-test, this is what I found. It allows us to sort of know exactly sort of what I'm talking about, what that means, how I ran it, and all that type of thing. Very, very important, because if Erica's version of the t-test is different than my version of the t-test, and Rachel has come up with something that she did completely made up on her own, it's hard to start sort of inferring anything about any other people's data. Okay, so this Wilkinson article, this is a fantastic article. I'm going to get this article tattooed on my back. It's just that good. A really, really nice way of going down through and thinking about, from responsible research science, how we sort of things that we should be using, things that we should not be doing in terms of falling into individual traps, right? And some things that come up in this Wilkinson article talking about a lot of times people get all worked up on statistical packages. For the stuff that we're doing this first semester, no one cares what statistical package you're working with. The t-test that Stata is doing is the same as the t-test as SPSS is doing. What we should be more focused on is knowing what these statistics mean, knowing how they're computed, how they're interpreted, right? You should never, ever just report something on a page without knowing what it means and how it was computed. Like, do not ever just report a statistic just because it happens to come up on an output. Just because you ran it and followed the steps that you were supposed to do to get there doesn't mean that what you've come up with is valid. You need to know exactly what's going on, what constitutes, what makes sense and what doesn't, right? That's on you as an investigator. We also want to make sure that our underlying assumptions are reasonable. Are certain assumptions for different tests? And say, do we have any sports fans in the crowd? Natalie, what kind of sport do you like? What's your?
I love baseball.
You love baseball. Okay. So let's say I've got a baseball game and I've got sort of Team A and Team B, and they're playing by the rules of baseball, and we see in a series one team wins 4-1. Who do we assume is the better team?
I assume the team that won games.
Won 4 games, right? But now let's go ahead and say, okay, we're doing the same thing. We got a 5-day series, except for one team has 3 more people than the other team, right? And they win 4 times 4-1. What happened to our confidence that that's a better team? It went down. And now what do we say? Okay, but then the other team, let's say they get to start with a runner on first base at the top of every inning. Now what happens?
Our confidence in their own goes down again.
Yeah, we start to lose confidence. So if we're playing by the rules that are set up, then we've got a pretty good sense of, okay, this is bigger than this, or there's an association of this or whatever, right? But if we start screwing around with the rules, right, and all of a sudden we say, okay, well, we're just going to call this baseball, but we're not going to play by the rules of baseball, right? One team gets to use one team is pitching a baseball, the other is pitching a softball. This team doesn't get a third baseman. This team gets 4 strikes instead of 3. Right? All of a sudden we're changing the rules, and now we can't infer anything that we would normally infer. This is essentially what we're doing with statistics. If we met our assumptions, and there's some assumptions that we violate, it's fine. But for the most part, if we start violating this, we start to lose confidence in that what we think is happening in this data is actually happening. So we need to be mindful of do our data fit the tools that we're trying to apply with things? Okay. So we're going to spend a lot of time thinking about assumptions. And again, when we start to get effects, we need to be thinking about, is what I found credible? Okay. Does this make sense? 2, does this generalize, right? Again, we got people coming in from a lot of different areas across the country. If I find a difference in 19-year-old males from Wyoming who are majoring in engineering, is that a sample that's going to generalize to all people in the universe? Maybe, maybe not. Probably not, right? So we need to think about, like, what did I find? Is that going to generalize, right? And then thinking about robustness, right? Is this something that I have a very, very weak signal that if I try and do it again, it's probably going to fall apart? Or is this something that's going to go through and I'm going to be able to find it again and again and again and again, right? Also making sure that we're pulling in previous existing theory and previous research. If there's been lots and lots and lots of studies, and all these studies have all kind of found the same thing, and then all of a sudden I find something completely different that's the exact opposite of anything that anybody's ever found, should I be suspicious of that finding? Absolutely, right? I might have just had a weird thing that comes up. If my data isn't consistent with what theory says it should be or what previous research has found, that should be triggering me to think carefully about sort of what happened with this, okay? So again, as people are working through, I think people get a lot of times worked up about the numbers. No substitute for thinking carefully about what we found, what the implications are, and how we interpret this and what it means for our given research question, okay? No one does statistics for their health. No one's just doing it to do it just because they love to just run random things mostly. I'm not saying never, like some people might. I sometimes would. In general, though, we're trying to answer a question about human behavior. We're doing this to try and say, what I'm interested in is whether or not these two things are related or how these constructs fit together. Is what I've got makes sense? And if I don't understand what my tools are and how they work and what their relative limitations are, what I can do is I can start reporting things that don't make sense and not know it, which sort of makes me look like I don't know what I'm doing, which by definition would be true if that's the situation you found yourself in, okay? So just wanting to think about all this stuff, okay? So some basic definitions, making sure we're on the same page. Populations versus samples. I'm going to have you thinking a lot about population. We don't think about populations enough when we're doing research in our area. We kind of gloss over this, and it's not good because there's a lot of stuff in terms of implications. If we're talking about a population, we're talking about all individuals, all units of interest in terms of our research. Okay, and this may, depending on the study, vary on size and focus. Okay, so someone give me an example of a population. Ariana, can you give me an example of a population? What would a population be?
A population would be like a student body
Oh.
of university.
Okay, perfect. Student body, University of Wyoming, student body, that's my population, okay? And if that's my population, I'm saying the only people I care about in the universe are just University of Wyoming students. Now, are we talking about on-campus students or are we including off-campus students?
I guess all students.
All students, okay.
And off.
On and off campus. Are we interested in graduate students? Or are we just looking at undergraduates?
I guess probably graduate students as well.
Okay. People who are part-time or just full-time students? All of them. Okay, you weren't even trying to fool me with this. When you said all students, you literally meant all students. Okay, cool. But these are the types of questions we want to ask, right? Erica, remind me again what your area of research is sort of looking at, sort of goal pursuit stuff. Is that right? Okay. And so let's say you're looking at a study on goal pursuit. Who's your population of interest? Okay, so we're sticking with UW, but underrepresented populations at UW. Okay, so now all of a sudden we need to start thinking about, like, what are we talking about in terms of underrepresented, right? So are there specific groups, are there specific populations? And this can be very small, just to maybe one specific group, or broadly defined underrepresented in a lot of different dimensions, right? And so we need to be thinking about this stuff. Some of our stuff that we're looking at, if I'm doing research on PTSD and I'm sort of writing a study about how X relates to Y, how PTSD relates to something else, who am I implying is my as my population? If I say PTSD is related to, holds this relation with social support, who am I implying that my population is?
Wouldn't it be like everybody with PTSD?
Yeah. I'm saying what I've implied there is that this is a fundamental and universal association between post-trauma symptoms and social support for all individuals who have ever been exposed to a trauma, right? But maybe my study is based on university undergraduates from PSYC 1000 courses. Now all of a sudden there's a disconnect here, right? And this starts to become important in terms of thinking about generalizability. Who is my population of interest? Who did I get? And what are the implications of that in terms of inference? Okay. So again, on the paper I'm having you read, APA Task Force, interpretation of results depends on the characteristics of the population intended for analyses. We always need to be specific about who am I talking about. I'm going to have you all do this over and over and over and over again. When we're talking about your hypotheses, I'm going to force you to say, what's the population? Who's the population of interest? And then that's hopefully going to force you to start thinking about, here's my intended population. Here's who I could get. What are the impacts on inference? Okay. So this is our population, our sample. These are the people who we could get, right? So this is who I would like to, can we ever get the population? Is there ever a practical situation where we get every single member of a population? Probably not. Not never, but it's it's asymptotically close to never, right? Because if we get the population, we don't need to do statistics. We just say, these are what all people look like, right? So what we need to do is we need to go through, because we can't get everybody, what we're going to do is we're going to select a sample. And then hopefully that sample is random, right? And hopefully that sample is large. Why do we want large samples? Brittany?
It represents more of your population.
Yeah, you get better coverage, right? I'm going to get more people sort of involved. I'm going to have greater precision just because I'm going to get a better sample. Same thing with random samples. They're better because I'm not systematically pulling through. If my population of interest is all people with PTSD who have ever experienced trauma, and my sample is University of Wyoming undergraduates, that's a problem because it's not a random sample, right? It's a very, 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 very infinitely specific subset of the population that may not generalize in all cases to the people who I'd like it to, okay? So wanting to think carefully about who's our population, what's our sample, and what does that have, what's the impact on our inferences, okay? Other stuff, variables. This is just characteristic condition that changes, has different values. If everybody in my sample has the same value, I don't have a variable, it's constant. That causes problems with it'll tank my model. Parameters, this is generally we're using parameter to describe a population. So if I'm talking about the average value of all people, if I'm looking at the average age of all residents of the United States, and my population is the United States, that's going to be my population parameter. Anything else is going to be a statistic. This is a characteristic that describes my sample. And again, the reason we're working with statistics is our population parameters are essentially unknowable. I will never know the actual true, all the way down to perfect precision, average age of individuals in residents of the United States, because there's no way to capture everybody, right? But what I can do is I can get a random sample, a large sample that does a pretty good job of sort of with reasonable precision getting me in there. Okay, Our descriptive statistics, these are our summary statistics, help us organize, simplify data. Our inferential statistics, these are going to be our tests that, assuming that we're falling within sort of basic assumptions, are helping us make generalizations about an intended population. So, if we're thinking about statistical inference, again, who we're interested in is this population, right? And our populations can be actual real life people. Let's say my population of interest is all people in the United States, all residents of the United States, right? That's an actual, like, technically I could, given infinite time and resources, that's a real population that I could capture, right? But sometimes my population is hypothetical. Let's say I come up with a new drug. Let's say, I found a vaccine for COVID, okay? And I go through and I'm testing people who got my vaccine for COVID and people who didn't get my vaccine for COVID. If I'm looking at the difference between those two groups, what are my two populations?
Is it those with and those without?
Yeah, can you say a little bit more about that?
Like, one population is people in America that don't have COVID, and one population is people in America that don't get the vaccine, and one that do.
Yeah, right. And so if we're looking at, if we're taking a literal perspective on this, right? And I've got, let's say, 50 people who got the vaccine and 50 people who didn't, right? Like, those 50 people who got the vaccine are all the people who got the vaccine, right? That's it, right? But I'm not really interested in those people. What I'm interested in is a hypothetical population. If I were to give this vaccine to all people with COVID, like, that's who I'm interested in making an inference of, right? And so same thing with some of our experimental studies. If you're looking at like spatial cognition or something like that, and you have someone going through like an experimental task or something along those lines, and you have 20 people who've taken that, right? Those individuals, that's not your population. That's just a sample of a hypothetical population of all people who could have taken that or performed or engaged in that task, right? And so wanting to think about sometimes we're talking about sort of real populations that actually exist in the universe, and sometimes we're talking about hypothetical populations. Like, if we were to apply this to everybody in the universe, that would be the population that we're interested in, okay? But the problem with our population is we can't get everybody. Like, we can never sample everybody that we're interested in. So what we do is we get a sample, okay? And this sample, these are the people who we're able to go through and test. So here's my population. Here's everybody. I'd like to have that. I can't. These parameters are functionally unknowable. Well, what I can do is I can go through and I can pull a sample. And what I can do with this sample is I can run tests on that sample. And I can start to measure that sample to start to try and infer something about that population. Okay? So the population itself, I will never know the true value in that population. But what I can do is I can get random samples and I can get large samples and start to get a very, very good close idea of what that value is in the population using some of our quantitative methods. Okay? So again, our procedures here are intended to draw inferences about a population based on the sample. People comfortable with this? It's a basic fundamental principle of statistics, but we forget it about it a lot of times, because the take-home message here is our hypotheses are never about our sample, right? I'll say, so I'm running a study and I'm saying that my hypothesis is that people in my no pain sample will have higher levels of trait anxiety than people in my no pain sample. Okay, what's wrong with that? We say that all the time. What's technically wrong with that statement of hypothesis?
Saying sample, right? Like, we're supposed to say population because you're using the sample to make an inference.
Yeah, perfect. Brittany, Do I need to run a statistical test to see if my levels of anxiety are higher in the people in my no pain sample versus my not pain sample?
If do you need to run a test to
Yeah. So my people in my no pain sample have a value of 40, or people in my pain sample have a value of 40. People in my no pain sample have a value of 30. Do I need a statistical test to tell me whether or not the 40 is bigger than 30? No, I don't. I can just say, so this is not about the sample, right? I don't care about the sample. The sample is just there as I'm using the sample. I'm using the sample for my own means to infer something about the population, right? So if I say I'm hypothesizing that people in sample A are going to be bigger than sample B, I don't need a statistical test for that. I can just see if those numbers are different, and if they are by that much, right? What we want to do is say, do we get enough evidence in these data to make the inference that people in the population A are systematically different than the individuals from population B in some way? Okay, so again, our hypotheses are always about whatever the target population is. And so if we start sort of forcing that into our brain, it's going to help us sort of make better interpretations of our data and things that are going to be more responsible. Questions about that? Cool. All right. So other concept we want to talk about is sampling error. Okay. Sampling error. And again, sort of burn this into your brain. Sampling error, when we're talking about sampling error, all we're talking about is the error, the discrepancy between a sample statistic and a population parameter. That's it. Okay. If we have a difference between our unknowable but hypothetical population parameter, whatever the value is in the population, if there's a difference between that number and the number we get from our sample, Robert, what do we have?
Sorry, Evan, what do you mean? What do we have?
Okay, so here's in the universe, here's the value, the mean value of my population, and I draw a sample and I get a value for my sample that's a different number. So if there's a difference between the population and what I've actually sampled, what do I call that difference?
Pulling error?
Yeah,
okay.
Yep. It's just the discrepancy. It's just a difference, right? And the thing to remember is with this is because our sample is designed to be representative of our population, right? We hope that we've got a large random sample that's representative, but it's impossible for our sample to exactly match the population of interest. It's always going to be off to some degree, right? If we carry that decimal out far enough, we're always going to have some difference, right? So what we never want to do is assume that, hey, this value that I got from my study in my sample is the exact parameter that I'm actually trying to capture. It's always going to be different, okay? So here's an example. We've got a population of 1,000 college students, right? And this is, let's say, like this is my population. These 1,000 college students are the only people who I'm interested in, okay? So this is my actual population. It's a small enough population so I can actually measure this. And let's say I find that the average age is 21.3 years, average IQ 112.5, 65% male or female, 35% male. Okay, so I draw two samples here, each 5. Are these good samples, Allie?
I mean, probably not.
Yeah, why aren't they good?
Because they're, first of all, like really small.
Yeah. Even if this is a random pulling from this, the fact that I only have 5 people isn't sort of boding well for this, right? But for sample 1 that involves Erica, Jessica, Laura, Karen, and Brian, we see the average age 19.8, IQ 104.6, 60% women, 40% men. Sample 2, Tom, Kristen, Sarah, Andrew, John, average age 20.4, IQ 114.2, 40% women, 60% men. Rachel, what do we have here?
Sampling error.
Ah, you guys are fantastic. Sampling error, right? It's not the same number as my population, so it's going to be different. And even it's not saying that I have a bad sample or that I screwed something up or that my sample is is biased in any way. It's just different, and it's always going to happen. Okay, but what
Ask a question.
yeah.
So are there acceptable ranges for sampling errors in studies, since it's impossible to actually not get a sample error?
Yeah, no, you're teeing me up for one of my favorite discussions on standard error, Robert. That's what we're sort of getting a sense for, getting an idea for if all things have gone well, sort of how far we're off with stuff. Okay, so what we can do though is we can start to think carefully about the different factors that impact my sampling error. Okay, factors that impact sampling error is sample size. Okay. Rachel, go back to you real quick. What's better in terms of sample size? What's going to reduce my sampling error?
Bigger sample size.
Bigger samples, and why?
Because it's closer to the actual population.
Yeah.
The more you might, eliminate random variants and things like that.
Yeah, I'm going to get a more representative sample if it's bigger because I'm going to capture more of the sample. As my sample size increases, my sampling error is going to decrease. It's not going to go away, but it's going to go down, right? We're also seeing, come on now, sample selection. What is, Natalie, my gold standard for sample selection? Random samples, and why? Why is if I have a true random sample, how's that going to make my my sampling error decrease?
It's going to be more representative population because you're not biased in selecting your participants.
Right. I'm hopefully with a random sample. Now, in theory, I can get a random sample that just ends up pulling just people from the University of Wyoming just because it's a weird 1 in a million chance thing. But in general, my random sample is going to have a better likelihood of capturing all relative parameters of my, or sort of areas of my population, and that's going to be important. Okay.
Can I ask you a question?
Yeah.
So, for example, we do, and this is me just probably not understanding. So, we want a random sample. So, if the kids who do SONA as undergrads, does that count as a random sample still?
Absolutely not.
Okay, I just.
Yep. I mean, and this is the thing that starts to become tricky, right? Because people are self-selecting into research, right? So one, it's not even a random sample of people who are in undergraduate psych courses who are offering credits, right? Because these are folks who have elected to go through, and probably it's going to be people who are just maybe more academically minded, sort of more organized and things like that. So we're starting to sort of pull stuff in. And so this is why, and we're going to talk about this a lot, that all the assumptions that our statistical models are based on, we systematically violate them in psychological science. And it's not because we're bad researchers, it's just because we're limited in terms of our methods. So we can't necessarily, there's things that we can try to do to mitigate some of that. But really what we need to do is be very clear in terms of the limitations of our methods. Okay. Another thing that's important is our measurement tools. What aspects of our measurement tools, Riley, might start to impact our sampling error?
I don't know, this could be completely wrong, but I feel like if the tool isn't reliable or valid, it's not gonna necessarily represent the population.
Yeah, exactly right. And we don't think about this enough, right? We just be like, oh, well, I want to look at sort of this construct or something like that. So I go through and I pull whatever the first measure that comes up that I'm able to get. I'm going to go ahead and use that, right? But if my measure is not reliable or valid, my sampling error is going to go through the roof, right? Now, let's say that I'm interested in the average weight of college students at the University of Wyoming. Okay. And let's say I've chosen for my measure of weight, I just have people come to the lab and I just kind of grab them around the arm and pick them up a little bit and it's like, this person's, call it 115, right? is that a valid measure of weight? It's not invalid necessarily, right? I mean, it's sort of kind of, it's going to be better than going with, like, say, shoe size as my measure of weight, right? It's going to be more valid than that, but it's not great, right? Let's say, so Kyle does sort of eating pathology, right? You have people coming up like, oh, I'm just going to sort of pick you up, kind of weigh and see about how much you weigh, right? That is a measure of weight. It is not a good measure of weight, right? If I have a digital scale that's a much more precise and valid and consistent measure of mass than my just kind of giving it a guess, right? And so that's going to be a better tool that's going to go through and reduce my sampling error. It's kind of a silly thing, but particularly for those of us who are trauma researchers, what's a better measure of post-trauma symptoms? A self-report measure or an interview measure?
An interview.
The interview measure by a whole lot, because there's a lot of stuff that people will report if you ask them about distress, that they'll report as distress that maybe not it's going to be trauma related. It's going to be other stuff, right? And so thinking about our measurement tool is reducing standard sampling error, okay? So again, the methodological piece of research is huge, and it's not independent from your statistics. If I've got really poor methods, I can't statistic you out of really poor methods. If your measures aren't good, if your sampling procedure isn't good, if your sample size is small, there's no correction that we can make that go away. That's just poor data, and so we need to be thinking about not only analyses what people did, but you're unable to divorce this from the methodology. All right, let's go through and let's go through this real quick. Other thing we need to be thinking about in terms of our constructs. If we're talking about a construct, we're talking about some attribute characteristic that we can't observe directly, but starts to become helpful for identifying or thinking about behavior. Allie, can give me some examples of constructs?
Let's see. So, like, just anything. I mean, like a personality test, or
I'll accept what is anything, Alex. Because you're right? Basically anything. So this I don't know if anybody's run into this before. Back, intelligence is just a construct. Everything's a construct. Time is a construct. Mass is a construct. Color is a construct. That's not a useful argument for anything, right? But it starts to become important to remember that what we are trying to measure in terms of our constructs and what we're actually capturing are two different things, right? And they're not one and the same. And so what we need to do, if we're thinking about my construct, is depression or goal pursuit or self-injury. My construct is spatial cognition, right? We're getting we need to give an operationally define what this is, right? So we're saying I'm interested in negative affect, and my operational definition of negative affect are X, Y, and Z, right? This is how I'm going through and defining this. This is how I'm going to measure it, recognizing that my construct of interest of negative affect may not be exactly what I'm getting with my actual measure. So just because I have a scale that says it measures narcissism doesn't mean that that's a pure measure of narcissism. Hopefully it gets at narcissism. Hopefully it gets at a lot of narcissism, but there's going to be other stuff that starts to come through, right? And the thing I would sort of want you all to remember as we're going through the semester, remember that our statistical analyses are performed on numbers. We're doing analyses of numbers that are imperfect indicators of our constructs. Okay, so let's say Allie's looking at post-trauma symptoms in first responders, right? What Allie needs to do is she needs to operationalize post-trauma symptoms. She needs to operationalize first responders. How do we understand these two things? Then we got to find a way to measure those two things. And then at the end of the day, we're going to run some analyses on these numbers. But these aren't perfect representations of what this scale says. Allie can come to me and say, oh, here's a PTSD scale. And I look through the scale and I'm like, well, just because you labeled it a PTSD scale doesn't mean that it's measuring PTSD, right? So we always want to be thinking about how are people measuring things and how does that relate to the construct of interest that they're wanting to look at. So let's say that my construct is academic ability or intelligence, okay? And my operational definition for my study of intelligence and academic capability is GRE scores, okay? Is my measure a good measure of academic ability?
Some people would say yes, but I would disagree.
Okay. And so then this starts to get into a debate, right? There's probably not, sometimes there's a good, what you got and what you're trying to measure are different things. That's not, right? But here we've got an evaluation that's specifically intended to try and capture academic capability or potential, but it's not 100%, right? So there's some differences there. What if I say my measure of intelligence is my construct is high school GPA? Is that a good measure? No, that's a worse measure. Natalie, I see you're shaking your head. Why is that? Why can't I interpret high school GPA as a measure of intelligence?
I think, different schools equate GPA to different things. Some people can get over 4.0. There's economic differences,
Yep.
resource differences, that kind of account.
1,000 different things, right? And I think this is one of the things that is hard for new graduate students, right? Because I've read a study, and that study got published, and that study said that they measured this, and this is how the two things relate to one another. You should never take any of that as face value just because someone said it. Like, you can get anything published. Like, I mean, if you try hard enough and sort of go enough spaces, right? Always wanting to say, okay, what are the claims? And is what they've done in terms of their methodology actually support the claims that people are trying to make here, okay? Again, our data, our analyses, our research is only as good as our methodology. We don't have any, can you just control for the fact that I've got a garbage measure? Like, no, I can't, right? I wanted to measure intelligence and instead I got GPA. Oh, can we statistically control for that to make turn GPA into a measure of intelligence? Nope, that you can't, because they're not the same thing, right? So as we're going through, again, I think people get, with quant methods, people start to get really sort of fixed with the numbers. And like, we got to go through and establish that sort of the measurements and sort of the methods getting there are reasonable before we can sort of do anything with the numbers, right? A lot of times when I'm reviewing papers, I don't even get to the discussion section because I'm like, well, the methods don't map onto what you're trying to measure. And so basically I can't interpret any of this stuff because you were trying to measure this and you had a research question about this, but instead your data are getting this. And so I don't know, I can't even say sort of what you have and what you don't have, right? So you all will go through, I think Kyle's going to be running methods this year, which will be, I think you're not in methods. Are you in methods this fall? Okay. You'll pick up methods then in the spring, but an important thing, sort of your methods and your stats go hand in hand, can't divorce the two. If I had to choose which one's more important, the methods or the stats, the methods are more important. Cool. All right, folks. Let's go ahead and stop there. What we'll do, let's take a 10-minute break. Let's be back at quarter after, and then we'll finish up. We'll get as far as we can with today's stuff. Cool. Cool. All right. Welcome back, everybody. We're back in the mix. Going to go through and finish up. So we've talked about, or I guess any questions on kind of the heady theoretical sort of concept stuff that we've covered up to this point in terms of populations, samples, constructs, sort of measurement types of things. Okay. What we can do now is start to get into more concrete things that are sort of less heady. One thing we want to be aware of in terms of, and I would say, remember when I told you didn't need to read that first Howell chapter? That was false. Read that first one. They're going to get into some of these basic things much more deeply in terms of basic terms in terms of level of measurement. When we're thinking about level of measurement, it starts to become essential to statistical analyses because it starts to direct us into what types of models that we can run. Who here is terrified that by the thought of in your thesis you're going to have to figure out what type of statistics you're supposed to run for whatever you're doing? Show of hands. Okay. It actually becomes pretty easy once you identify what your research question is and what your level of measurement is. All of a sudden it starts whittling it down pretty quickly. But we need to be careful in thinking about what our construct is. We've identified that. Now we've got a measurement. So what's the level of measurement here? If we're talking about variable types, broadly speaking, we can switch things over into discrete variables and continuous variables. Can someone tell me what the difference between discrete and continuous is? What do you think, Robert? I'm going to pick on you just because I saw you in my screen here.
So I guess like it would depend on like what sort of data like you're collecting, and like as in like categorizing it, or if it needs to be on like a certain time frame or whatnot, and then I guess like continuous would I guess that would be just more like on like time bases and whatnot.
Okay, so time is a good example of a continuous measure. If we think about discrete just means a categorical variable, right? Things that come in sort of separate chunks. Continuous variables are things that have an infinite number of possibilities between. So we can break it up into increasingly small chunks, right? We can go through, and so if we're thinking about discrete variables as categorical variables, continuous as sort of literally existing on a continuum, we can further break this down into nominal scales. Nominal scales are going to be things that have no order. They're just different categories. Natalie, can you give me an example of a nominal variable?
Maybe like gender.
Actually, gender is kind of a tough one. Gender, actually, we think about gender as in terms of a construct is on a continuum, right? What about what would we measure as a nominal variable? Not gender, but
Biological sex.
Biological sex, and even that starts to get sort of tricky. Sort of you get folks with some ambiguity in terms of biological sex assignment, but in general, we can think about sex as a nominal variable, right? So it's one or two in terms of biological sex. What about anybody else having an example of a nominal variable? Okay, ranking is going to be a little bit different between. What about car types? Okay, if we say builds, right? So we got Ford, Chevy, Nissan, BMW, so it's just different things, right? We could say these are types of soda, things along those lines, right? So nominal variables are going to be categorical variables where there's no order. We can sort of flip them all around. It doesn't matter. They're just distinct categories, okay? What about ordinal variables? What are we talking about here?
Would this like be more like rank?
Yeah.
So like you have an order like things that are different, but they might not be like it's not like a certain like the difference isn't always the same.
Yeah, exactly. Right. We've got something that I can rank in order, right? As this is lower than this, right? But there's not a systematic sort of the difference between 1 and 2 is not the same as the difference between 3 and 4 is not the same difference between 6 and 7, right? And what types of measures are often on ordinal scales?
Maybe something like a mood measure.
Yeah. Rachel, you're right on target. Almost all of our stuff that we do in psychology is technically an ordinal scale, right? Because I have, okay, rank this on sort of a 1, 2, 3, 4, 5, right? I can do it if I'm sort of saying like extroversion. If I'm low on extroversion, if I rank 0 means like not at all, 5 is a lot. We're assuming that the people who rank 0 are different than the people who rank 5, but the difference between 0 and 1 and 2 and 3 and 4 and 5 aren't all the same, right? They don't have intrinsic meaning. I can't sort of the difference between 1 and 2 isn't twice the difference between 3 and 5, right? And so almost all of the things that we get in our self-report surveys are almost always ordinal. There's ordered categorical data. Now, once we get ordered categorical data that start to get big enough in terms of the number of categories, we treat it as ordinal, or we treat it as continuous, which is why I've asterisked that there. But if we're being very careful about it, so we recognize that the measurement that we're getting is probably ordinal. It's ordered categories. Okay. Then we get into our continuous scales. Continuous scales can take on any value between sort of the max and the minimum. You can literally sort of cut it down into increasingly small units. All the units are equidistant from one another. If I weigh 200 pounds, I am literally the same amount bigger than someone wearing 190 pounds as someone who weighs 50 pounds versus 60 pounds. It's the same no matter how we go through and do it. And I can, with increasing precision, I can get this smaller and smaller and smaller. The only difference between an interval and a ratio scale is the presence of an absolute 0. Okay. If I measure let's say temperature in degrees, right? Is temperature in degrees Fahrenheit? What type of scale is that? Natalie?
Interval.
Yeah, it's an interval, right? If it's 0 degrees outside, who here's from warm weather climate? We got people from Arkansas, we got people from Texas. Yeah, it'll get 0 degrees here. Does that mean that there's an absence of temperature? There is no temperature outside. No, there's still temperature. It's just not. 0 is just some point on a scale, right? But the difference between 10 degrees and 20 degrees is the same as 90 to 100 degrees. It's all the same. Our ratio scales, these are scales with true zeros. Like if there is 0 means the absolute absence of sort of that construct. Okay, so thinking about our variables in terms of being categorical or continuous. Now, sometimes we can treat our categorical variables as continuous in some situations, and we'll talk about this. But the other thing that we want to be thinking about too is thinking about the difference between the level of measurement of our construct and the level of measurement of our actual sort of assessment or observed scores. Those can be two different things. But just wanting to go through and make sure you're very clear on level of measurement, because this is going to have important implications for what type of analysis you do and how you're going to go through and interpret and critique. Questions here?
What is an example? Maybe I missed it. What is an example for ratio?
For ratio, mass. Let's say if something weighs 0 grams, it has an absence of mass. It functionally doesn't exist. So we're talking about 0 as a complete absence of something. Another one you'll use is like 0 degrees Kelvin. If people have taken chemistry, like at 0 degrees on that temperature scale means that like there's 0 molecular movement. There's sort of absence of stuff, right? And so what we're looking at there is things with an absolute 0. I mean, you could think about income, right? Technically, income is a continuous scale, where if I literally have 0, it means I have sort of no money, like literally 0 money. I can break things into fractions of pennies and things along those lines. So that would be another example. Does that help? Cool. All right. So again, this level of measurement is going to be important for selecting what type of analytic approach you're going to be using. All right. So once we've got our measures, right, what we want to do is be able to go through and run some basic descriptive statistics. And one of our sort of most primary descriptive statistics, something we want to do is a collection of metrics that we would refer to as our measures of central tendency. So if I'm looking at a measure of central tendency, what I'm looking at is some number that's the single score that best defines where the middle of my distribution is. Like, what's the most representative score in whatever variable it is I've collected. So the idea is finding that middle. What's the most representative of the whole group? If I had to say, what is the number that best represents sort of this sample that I've got, this is going to be your measure of central tendency. And this is the measure that's going to be sort of what we're using this semester to look at between within group comparisons. We're going to say, okay, this group has this measure, this group has this measure. Do we have enough evidence to suggest, based on these data, that these populations are actually different, maybe in some way? Okay. Bad news is no single method for determining what's the best, right? This is where your knowledge of your methodology and your measurement has to come in to try and choose which of the different metrics of central tendency, which one is going to be the best for your purposes. So here, Erica, where would you say the center of this distribution is?
100.
Yeah, 100. How did you come to that conclusion?
The peak of the bell curve is at 100.
Yeah, the peak of the bell curve is right there, and everything kind of falls down, right? So pretty easy situation there. Rachel, what about here? Where's the center of this distribution?
0.
Maybe, right? What might be? Why might I criticize your measure of central tendency at 0?
Well, I guess maybe frequency would be 0.
Frequency, 0 is good for frequency, but if I want to say the whole distribution, what's the best measure of the center?
Probably close to, I don't know, -1.
Yeah, somewhere in there, right? So it starts to become a little bit more ambiguous about what the most representative score is going to be, right? Riley, what about this one? What's my most representative score here?
Well, this is the one I didn't want. Like that bar right above 140, maybe. So, does that sound wrong?
Well, I don't know. Sort of what if you get that the bar that's just above 140, what this looks like there's a lot of scores above that, right, that aren't being captured by that score. What do we have going on here?
Measuring body mass.
Yeah. And how would we describe this distribution? Anybody? Natalie? Bimodal. Yeah. And what given what we're measuring, what might be going on in my sample here? So we got some people that are kind of sort of falling around this one little sort of 150-ish area, and then another group that's falling around 180. What might be going on?
Might be measuring genders or sex.
Yeah.
It's
Yeah.
actually-
What I might be now, I don't know, sort of grams probably don't map well onto human beings, right? But what it looks like to me, and anytime we get a bimodal distribution like this, I start to worry, or I start to wonder whether or not I've gotten not one population, but two distinct populations here, Riley. So this is tricky, right? Because if I were to take the mean of this, Riley, where's that going to fall? Ish.
In the middle, like 160?
Yeah, somewhere around that 160, right? So if I just calculate the mean of my sample, I'm going to get something that's probably around 160, 165, something like that. Riley, is that a good measure in terms of if my goal of central tendency is to get a good representative number for my sample?
I feel like no, just because there's like less than 20 people who have that weight.
Yeah. What I've done is I've calculated a measure of central tendency that's a pretty poor measure of anybody who's actually in my sample, because not many people are in there, right? And so what I need to do is think about, like, how do I go through, given the distribution, how do I choose a measure of central tendency that makes sense and achieves my goal of describing or summarizing what's going on in these data? And so here, this could be, if this was sort of real life human numbers, it's a little bit distinct, but I might have men and women, right? Different here. Or if this is some sort of rat research, I might have two different species of rats, right? Or two different treatments. So it looks like there's two different things going on. So anytime you see a bimodal distribution, first thing you should be thinking about is, did I accidentally capture two distinct populations here? Because they look pretty separate. Okay. So when I'm choosing a metric of central tendency, I'm going to be basing my decision basically on the shape of the data and the type of data that I'm working with. Okay. First, and our most common measure of central tendency, probably at least in psychological statistics, is going to be our mean. You'll hear in statistics writing, your mean is your first population moment. This is just your arithmetic average. We're just taking the sum of all the scores divided by the scores. This is going to give you your mean. You've been doing this forever, since grade school, calculating averages. Nothing super fancy about just your straight up mean. Now, we can also have weighted means, okay? And weighted means, this is an approach that we're going to use when we're trying to find the average or middle point of two different samples, okay? And here we're going to take the sum of our first set of scores plus the sum of our other set of scores over the total number of scores in our sample. Important to recognize that your weighted mean is not the average of the two sample means. So if I have a sample of 50 people and a sample of 100 people, and the mean of one is 40 and the mean of the other is 50, my weighted mean is not 45, okay? What we're going to do, so let's say I am looking at measuring the same thing across two different sites. I've got a collaborator at where's Allie? At Fake UW. And I've collected 50 people, and my collaborator, Allie, at Fake UW has collected 100 people on the same thing. Which one of those samples is more representative and sort of a better measure of whatever it is that I'm looking at, Allie?
Sorry, where was the other sample here?
So I've got one sample here that was 50. The sample that you collected in Washington was 100. If we're measuring the same thing, what's a better sample?
The one in Washington.
The one in Washington, not because Washington's a better institution, but because you just collected more people, right? And so what ends up happening then is we want to give that a greater weight because they've got more people. That's a more precise sample. If we just average the two means, then we're sort of weighting those equally, and that's sort of not the case, right? So we'll work with weighted means a little bit, but just recognize that if you've got samples of different size. Now, Ali, if I collected 100 people, you collected 100 people, can we just average the two means of those? Well, if we've got exactly the same number of people, then we can just take a shortcut and just average the two means of the two samples because they've got an equal number and it'll turn out arithmetically to be the same, right? But in general, it's rare that we rarely have the exact same number in both cases, right? And so this is where our weighted mean is going to take into place. Okay. So characteristics of the mean. Each score, and this is a positive thing about the mean. So one of the benefits of using the mean as our measure of central tendency is every score in the distribution contributes to that value, right? No one gets left out. Everybody's score is counted in when we go through and calculate the mean. And if we go through and we change a score, it's going to change the mean. If we added a new score, it's going to change the mean, okay? Except for when. When does changing a score or adding a score not change the mean?
When the same number is added to all the numbers, right?
Okay, yeah. So that would be, if we add a constant, that'll shift it. But in general, if I say I've got a sample of 100 people and I add someone new to the mix, that's almost always going to change the mean, right? Or if I have a sample of 100 and I change somebody's score, that's going to change the mean. When is it not going to change the mean? What if the new person has the exact, their score is the mean? Then it's not going to change, right? If I've got a sample of 100 and my mean is 50, and I add Allie and Allie's score is 50, then she doesn't change the mean, right? But in most cases, if you add or subtract or change a value, it's going to change the mean. And when in applied stuff where this gets to be a headache is, let's say you ran a bunch of numbers and then you realize that you should have excluded these two people. What's that exclusion of those two people going to do to your mean? It's going to change it, right? And so then I have to rerun my analyses because I've got a different mean for that, right? So recognizing that a benefit of the mean is that everybody gets included, but if I add or subtract someone or change a score in there, it's going to change my mean. Okay. If I've got a situation where I take a constant and I add, subtract, multiply, or divide every score in the sample by that, it's going to change the mean value by that number. Okay. So again, this starts to become relevant when we're doing scaling for different types of statistical procedures. If I've got a sample and I measure people's height in inches, I'm going to see here, this is people's height in inches. But what do I need to do in order to get height in, if I say, I don't want to work with inches, I want to work in feet? What do I do, Robert?
And scale it up proportionately because you would know that you're changing it all value. Yep.
I'm going to take in my sample. I've measured people's height in inches. I'm just going to take everybody's score. I'm going to divide it by 12. And so if my mean in inches was 48, and then I divide all of them by 12, my mean in feet is going to be 4 feet, right? We're just going through and taking that mean, dividing it by 12. Same thing. Rachel, if I have, here's my original data, and I add 2 to everybody's score, what's my new mean?
Sorry, I had to remember to unmute. 50?
50, yep. It's just going to change it up. If I subtract it, if I multiply it, we're just taking that mean number, multiplying, dividing, adding, subtracting by that constant, and we're going to go through and do this. And so this starts to become an issue in scaling, and you can back translate stuff in terms of mean values, right? Let's say that you have someone reported, and this will happen, someone misreported a measure that you use, and they reported a total score instead of a mean score. Can you still get the mean score off of that? Yeah, because if you know how many items are in the measure, you can just divide it by the measure of items and you're going to get the mean score for that. So you can go back and forth with mean stuff, okay? But If we go through, we add, subtract, multiply, or divide each score in the distribution by a constant, it doesn't change the shape of the distribution. This is an additive function. The distribution of my scores in inches are exactly the same as my distribution of scores in feet. One and the same, doesn't change anything going on there. Okay. All right. But we have other options. We don't always have to use the mean. We can also use median values. Median values is going to be the middle score. It's going to be the score that if I line everybody up in order, the median is going to be the direct center. It's so that half of the sample, half of my scores are above this value, the other half of the scores are below this value. So here we've got a collection of 15 scores. What we've done is we've put them all in order. And then we say, okay, here's the bottom 7, here's the upper 7, right here in the center. This is the middle score. This is going to be my median. Okay. So with an odd number of scores like we have here, it's just going to be the middle score. Here's the lowest, here's the highest, here's the middle score. If I've got an even number of scores, what I can do is list them from highest to lowest and select whatever the middle pair is, or sometimes take the average of whatever that middle pair is. It's possible that in these cases my median value may not be an actual score that I observe, but it's just how we go about calculating median. Okay. So people see the difference between the mean and our median? Okay. Other option we have is our mode. Mode, pretty straightforward. Mode is just the most frequent, or the score with the greatest frequency in our data. Okay. Mode is great. Mode can be used with any scale of measurement. Doesn't matter. Super helpful. If I want to take the mean of brands of toothpaste, does that make any sense? No, it doesn't, right? If I ask people, so what's your favorite type of shoe brand, right? And I'm going to go through and take the average of your favorite type, but that doesn't mean anything, right? What I can do is I can take your mode. So this is the modal shoe brand that people selected as most commonly as what they preferred. Okay. Other thing though, the thing we need to recognize though is that with mode, we can have distributions with clear multimodal distributions where I've got multiple modes. The example I tricked Riley with had multiple modes, right? There's two distinct humps there, and so we can have bimodal distributions, we have multimodal distributions, and oftentimes that's indicative of potential multiple populations being pulled in. Okay. If I have sort of multiple modes, what I can start doing is we can start talking about relative modes, talking about major mode and minor mode. Here, I've got a major mode of 4 drinks. My minor mode is 0, and then everything else is kind of sort of whatever. So major, minor modes is terms that we can use to start more easily sort of specify sort of which one is technically higher than the other. Okay, so we've got a lot of different options. How do we decide to go through and choose our measure of central tendency? In general, for the types of analyses that we're going to be doing this semester, our mean is going to be what we're working with in almost all situations. Okay, mean is typically going to be the most representative value for the set. Again, every score contributes, so everybody gets a say in terms of the middle value. What we see is greater stability across samples of the mean relative to the median and the mode, because our one score can start to change that median around, right, where that middle number is. What we tend to see is the aggregate, sort of the average starts to be more consistent. It's not going to be exactly the same, but we're going to see that jump around less than the median, and particularly the mode. Particularly if we've got a lot of scores that are kind of in the same area, right? Sort of the mode can jump around quite a bit. Mean tends to be pretty stable, and our mean serves as the basis for most of our inferential statistics. Okay, so median is our mean is going to be what we're going to be using most of the time. Problems with the mean though, it starts to be easily influenced by extreme scores. Okay. Ari, why is the mean start to be more vulnerable to being pulled around by extreme scores?
Just because it will, if you have like an outlier, it will start to kind of just pull the mean.
Yeah.
That wasn't really answering the question.
Nope, that was perfect, and you're exactly right. Depending on what my scale is. Now, in psychology, a lot of times we're saying, okay, here's on my 0 to 10 scale, right? And so, like, you can only be so far above the mean, right? But as soon as we start getting into other constructs like income, I can be exponentially higher on income than somebody else. And if I've got a small sample, that can start dragging that mean all over the place, right? And so a benefit of the mean is that all scores are included. A downside of the mean is that all scores are included, particularly if I have outliers and you start dragging stuff around. Now, the mean might not actually be an observed value, right? I might have a wonderful distribution, right? A very nice normal distribution, but my mean is actually a value that no one actually falls on because no one specifically had that value. That doesn't necessarily mean it's bad. It's just that sort of my mean is 45.7, but there's no one in my sample who actually has a score of 45.7. Usually not a big deal, but something to think about. And then again, the interpretation of the mean assumes that we have some interval level of data. Okay. If I'm going to give a literal interpretation of the mean, it assumes that whatever I'm measuring can take any value between sort of the min and the max, right? So if I say the average number of children in the U.S. Is 2.5 kids, is the mean a meaningful measure of central tendency for number of children? Natalie, you're shaking your head. Why?
It's a half child doesn't exist.
Yeah, we can't. We have no half children that sort of we can have that's sort of existing in the world, right? And so we need to be, if we start to think carefully about sort of, is the mean a reasonable number of this, or a reasonable measure of central tendency? Okay, so limitations of the mean. So maybe we go to the median. Okay, median can be a nice alternative under a lot of different circumstances. One, if I have skewed data. Okay, I have meaningful values in there that are real values and values of interest, but they're just a little bit extreme. Okay, so Erica, if we're looking at these distributions, why might my median be a better measure of central tendency here?
Because it takes in like both sides of the extreme.
Yeah.
Yeah.
Yeah. So I'm not sort of my mean is getting pulled out towards the end, right? Because those extreme values are starting to pull that out. My mode is on the other side. My median kind of right there in the center in the middle, right? And so in the cases of skewed data, that median starts to be a better representation of maybe the middle of the distribution than either the median or the mean or the mode. Okay. What about a situation going on here? Again, Erica, is the mean going to be a good measure of central tendency for these data?
Maybe.
Well, if we have a lot of scores, right? But here we only have about 4, 1, 5, 8, 9, 10 scores. What's this guy here on the out going to do to my average score here in this distribution? Yeah, it's going to drag it way out, right? I'm going to have an average value of maybe like, say here, 60. Is that a good representation of this distribution? No, right? But if I go through and I capture the median, my median is going to be so right here at 20 or 30 or something like that, right? So my median is nice because it's not as susceptible to some of these extreme values. Okay? Another place where the median can be helpful is if I'm using censored data. Does anybody know what censored data are, or what censoring refers to?
If you remove someone,
What's that? All right.
if you remove someone from your data set, or if you remove people.
Okay. Not quite. Yeah, so this is going to be excluding people from the set. If I'm talking, what's going on with this set here? So I didn't remove anybody, but what's happening to my scale? So I've got miles per day, and technically miles per day driven is a true ratio scale, right? If I travel no miles in a day, it means I didn't go anywhere. I can sort of infinitely go, and so there's each sort of difference between each one of these. So it's a continuous scale, but what did I do at the top of this scale?
Are you asking anybody to?
Yeah.
You stop, like, under 100 it goes by like nines, and then 100 and over is like, there's no, it could be anything.
Exactly, right. Brittany, based on these data, if this is how I've coded it, can I calculate a mean score from this?
No, because technically those three, you don't know if it's like 100 or 250.
Exactly, right? So I don't know. And so this is what we talk about in terms of censoring. If we've got sort of a X and below or X and above, that's a censored variable where we just said, well, anything above this level, we're just going to treat it all the same, right? And so what we can't do is we can't go through and calculate a mean, but what we can do is we can calculate a median. We can say, okay, well, there's 3 scores that are apparently sort of higher than this. So we can go 3 in. We can still count that median score accurately, and so that's going to be helpful in these types of data here. Okay. Also, if we've got data that involves ordinal scales, technically, if we don't have equal space between our values, we technically can't calculate an interpretable mean because the mean assumes that the differences in the intervals between all of our scales are all going to be the same. Okay, so if I have a measure of anxiety, right, and I'm having people fill out a 20-item measure, and it ranges from 0 to 100. Do I know that the difference on my scale between 20 and 25 is the same sort of meaningful distance in units of anxiety as 95 to 100? No, I can't infer that, right? What I've technically done is I have an ordered cat. I'm assuming that 95 is higher than 90, but there's not a specific, I can't say, it's not like something like temperature or height or mass, where I can say the difference between all units is equally the same. And so technically, mean starts to become problematic there, okay? Our median doesn't assume equal intervals between values. Now, again, we treat our ordinal scales often as continuous, but technically we need to be careful and recognize that we're making some assumptions there. Okay. Does that make some sense? Cool. All right. Another thing to remember is that when we're running through our analyses of transform data, sometimes people love transforming data. Sometimes it's necessary, sometimes it's not. Technically, when we're looking at the analyses of transform data, we're looking at differences in medians. Okay, our transforms, they go through and they change the shape of our distributions. That's what these nonlinear transforms are supposed to do, but it doesn't change the order of the scores. If I log transform a scale, whoever's at the median is still going to be at the median with the transform scale versus the raw data. Okay, and so when we start to run means-based analyses using transform data, technically what we're doing is we're looking at a comparison of medians. Okay. So again, Allie, you had said that you had done some sort of alcohol substance use stuff. Ever done that in lab before?
Yeah.
Yeah, okay. So what we've got here is actual data from our undergraduate population looking at audit scores. This is the alcohol use disorder identification test, I think, yeah. So these are audit scores, and these are our raw scores, and this is pretty skewed, right? We've got most people not drinking a whole or having pretty low scores. We've got some people with pretty extreme scores, maybe what I say is I don't want to run this because I think there's too much skew. And so what I do is I take the natural log of all scores in my sample, and I get a new distribution. Allie, which one of these distributions do I like better in terms of approximating something normal?
Probably the transformed one.
The transformed one, right? But if I go through and in these data set, so these people, whoever are right here at this value, let's say it's 2, right? And these are, well, no, it's actually 3 because I have it right there, okay? So the median of my raw score is 3, okay? And the median of my transform score is 1.1, but all the people who had a score of 3 in my raw data set, all those people are at 1.1 here, right? So the median stays the same. It doesn't change around even though I go through and transform and get this adjustment going on here, okay? And we'll talk about this more when we get into transforms and other types of things down the road. Last thing we're going to do, just finish up because mode is pretty quick. Mode is great as a measure of central tendency when I've got nominal scales. When I'm measuring things that sort of only have sort of membership in some sort of category, so ethnicity, major vehicle presence, things like that. If I've got a truly nominal scale, median doesn't make sense, mean doesn't make sense. Your mode is really what you're going to want to use in most cases there. If I've got discrete ordinal count, right? If I have whole indivisible numbers going back through, technically mean doesn't make a whole lot of sense in terms of a measure of central tendency for the number of children people have in their homes. Mode might be a better one because we can say this is the most common number of children that people have. Now, that could skew out and sort of maybe median is better, but mode makes more sense than a mean would here. Same thing, Tara and I just bought a house. We're trying to get sort of all moved in and stuff like that. You say, oh, houses have on average 5.3 rooms. Well, I don't know what 0.3 of a room is. That's not a real thing to have, right? But I could say modal number of rooms in houses in Laramie is X, right? So that can help with count level data. And then using mode as a supplement to mean and median, if I'm trying to describe the shape of a distribution, again, rather than going back to that distribution I had you jump in the middle of, right? I can calculate the mean and I can calculate the median, but neither of those were going to be very good. I can report those, but then say, so here's the mean, here's the median, but this is actually a bimodal distribution with a major mode at this area and a minor mode at this area, right? So using mode is kind of a supplement to distribution that kind of have a funky shape that's still important to capture, but sort of maybe not something that's captured neatly with measures of mean and median. Okay. All right. That finishes measures of central tendency, which is a good place to stop here. Questions, thoughts, comments, concerns, anything about material that we went through in the lecture, sort of what things are going to be looking like moving forward in the semester, anything along those lines? No? Okay. You guys are superstars. Thank you so much for linking in, sort of being attentive, sort of bearing with me as I sort of ask you to answer questions you don't know the answer to. This is what I'll say. I know this is stressful, but I think this is a good skill to have, to be able to go through and come through with sort of reasoned guesses, because a lot of times your incorrect answers are more valuable than the correct answers, because if you were off base, I guarantee some, if not all of other people were also off base. So just do your best as we're going through. It's also because I'm an anxiety guy. It's a nice social exposure, right? It just sort of gets used to, it's okay to be wrong. Sort of be wrong with conviction, but be open to corrections. If you're wrong, be wrong with conviction, but then sort of if you get corrective information, make sure to incorporate that. Don't sort of proceed with being wrong. That happens sometimes. But Thanks again. If you have questions, let me know. Get in touch with CJ or I. Otherwise, we'll jump back in and finish up this introductory stuff when we meet next Wednesday. Sound good?
Thank you.
All right. Thanks, folks. All right. We'll see you later. Have a good night.